warm welcome to all of you from IonQ. As you may know already know, we build quantum computers from atoms, ionized atoms, and we're also focused on commercial applications. In fact, today it'll be my pleasure to share with you one of these applications that we collaborated with Airbus, a combinatorial optimization use case with inequality constraints. It's not moving forward, is it? There we go, okay. So my name is Nicole Barberis. I'm the Director of Sales Engineering. I've been involved in quantum computing for about 10 years, previously with IBM Quantum as a quantum machine learning developer, and most recently with IonQ for about 2 years. Today I'll also share with you some of the reasons why IonQ is very different than other quantum computing companies, in particular around our scaling and roadmap. In fact, this is why Time Magazine nominated us as a very influential company in 2022. Okay. There we go, that's better. All right. So why are clients gravitating towards IonQ? Certainly, trapped ion technology offers many unique advantages. Let me point out just a few in the next couple of slides. One is the quality of our qubits. We use naturally quantum objects, right? Ionized atoms. They are identical. In fact, they are fungible. They are not manufactured. This is very, very different than other modalities such as superconducting qubits, where each one is individually manufactured and engineered to exhibit quantum effects. So this manufacturing process introduces errors that I, as an application developer, and yourselves need to account for somewhere along the line, right? And I'll draw your attention next to that image there where the ions are in an array, right? They're held in a vacuum with electromagnetic forces. Notice that there are no wirings. This is very important to the application developer and for your results in the end. What this means is if you would like to entangle any of those two qubits, you do that directly. You do not need to introduce extra code in your program, no swap gates. So not having to introduce those extra layers of code means that you have a lower error overhead overall. And I'll draw your attention finally to the capability of running at room temperature. This is directly attributed to the fact that we do not use dilution refrigerators. Now take a look. You see the IBM engineer inside a dilution refrigerator casing. This is for 1 qubit. So you can imagine that this design of a quantum computer gets larger and larger. In fact, the image in the middle is the Google conception of a many, many qubit system, and look how large that is. IonQ is headed in the opposite direction. We are going smaller, modular, room temperature devices. In fact, we are just opened a new facility in Seattle where we will be building rack-mounted systems for your data centers in the future, right? This is included in our roadmap. So we have a very, very different architecture and design for scalability. Now, a few more comments around our qubits. One, I mentioned that we're using quantum objects, but what about coherence time? You as a developer are going to care very much how long your coherence time is, because that means how long your quantum effects are available in your program. In fact, I don't worry about coherence time. We have very long coherence times in the labs and in production systems that we deploy, right, as long as minutes. Now, what about gate fidelity? Our newest system, IonQ Forte, right, has very good gate fidelities. In fact, I'll showcase that in the Airbus example. And last but not least, spam, right? State preparation and measurement errors. When you run your code on a trapped ion system, you don't need to worry about this at all. They are practically zero. So what I'd like you to take away from this slide is the quality of the qubit really matters to the application results at the end. Now, around our architecture, I mentioned that there is no wiring between the qubits, right? But let me focus on the modular and scalable. How are we going to network these chips, these QPUs, right? IonQ's design includes using photonic interconnects. This means that you can use the photons, the interference in the photons, to entangle two qubits on distant chips, on two QPUs. Now you can imagine networking 100 of these. The way to do that includes current technology of optical switches, right? Multi-port optical switches. So this is what lends us to have a robust roadmap for scaling our systems. And speaking of the roadmap, I wanted to share with you some of our progress related to these advantages in the trapped ion technology. In 2023, we delivered 29 algorithmic qubits, and I'll say more about that particular metric here in a minute. We delivered this 7 months ahead of schedule. In 2024, we'll have 35 algorithmic qubits, but notice in 2025, 64 algorithmic qubits. This is where IonQ is expecting to discover quantum advantage, in particular for machine learning. And that mark is only 2 years away. That is also when classical simulators are no longer able to represent those states on a classical system. So in about 2 years, we expect to see some very exciting results. We have hints of these results already in quantum machine learning, where the quantum model is more compact, needs less parameters in the optimization landscape, and also less iterations. So I mentioned algorithmic qubits. This is a metric that IonQ is proposing to our clients. It is wonderfully friendly to developers, right? With one number, let me give you an example. If I tell you that IonQ Forte offers 29 algorithmic qubits, you as a developer can immediately make that useful. You know that with 29 good qubits, you can size your input data, right? Your input data structures. If you square that, so 29 squared around 841, that immediately tells you the depth of your circuit. You can employ as many, right, in the ideal case, as many as 841 entangling gates in your program. So we use the 2-qubit entangling gate as a measure because that is the more costly. When you're trying to design your algorithm, you're trying to count your 2-qubit gates. Lastly, we find this to be very client-centric, very business-friendly, especially when you think that quantum volume gets more meaningless as systems become more powerful and more mature, right? The more qubits you have, the more difficult it really is to understand what quantum volume is giving you, whereas algorithmic qubits directly communicate about the application performance regardless of the hardware, the underlying hardware. Now, along those lines, just a quick, please take a picture of this because in the very bottom there's a reference to the paper that talks about these benchmarks. What you see here is a comparison between trapped ion systems and superconducting systems. Blue means very good, close to ideal results. Red means noise. And a little bit further, on the y-axis, this is the circuit width and tells you the number of qubits available in that system. And you can see that between IonQ Aria and IonQ Forte. I was really happy to see in the previous 2 presentations a lot of IonQ use on IonQ Aria. So in the future, you'll be able to run these also on IonQ Forte. And of course, this is comparing to superconducting qubits through IBM and Rigetti. Now, before I go into the details of the Airbus use case, I wanted to give you an overview of the type of things we're doing at IonQ. We have chemistry, of course, and chemistry and materials science, 3D object detection using LiDAR data, 2D image classification using pixel data, then also several use cases around correlation analysis with copula functions using time series data. So I want you to take away this message that there are many, many types of input data that we can now map onto a quantum circuit and model these types of problems. So it is now my pleasure to talk to you more specifically about the Airbus use case. This is a combinatorial optimization use case with many inequality constraints. In particular, this use case is around loading cargo onto an aircraft. Now, why this matters to Airbus, certainly it's about lowering optimization costs. They also have an interest in making progress in their sustainability goals. Why this is news, it is the largest variational quantum optimization problem using 28 qubits. Earlier, actually yesterday, I was listening to some of the presentations. Some had 7 qubits, some had 8 qubits. This is with 28 very good quality qubits. The value in approaching this on a quantum computer is because the classical method for solving this optimization problem scales exponentially as you add more cargo onto the plane, right? And the heuristic method, which is employed these days, doesn't always guarantee an optimal result. So the question was, could a quantum computer do better? And in fact, we do have indications that yes, it will scale, and yes, it will give you some very good answers. And I'll show you this prototype. First, let's frame the problem. So in this situation, in this graphic, you see there are 3 types of containers, right? The type number 3 fits in 2 slots. Type number 2 instead fits in only, 2 of them can fit in 1 slot. So you can see that this is a problem around placing the right containers and the right slots in the most optimal configuration. In fact, before I move on, that line in the middle, the 0x equals 0, that is the center of gravity, center of mass for the airplane. So what are the constraints? Constraint number 1, the total mass should not exceed the maximum loading allocation for the aircraft. This is the constraint that lends this problem to be mapped onto a quantum computer. And that's because the classical, this is a variation of the knapsack problem, right? Which many of you know is an NP-hard problem and scales exponentially on a for classical systems. So that really is the heart of why Airbus and IonQ teamed up together to map this onto a quantum circuit. Now, the second constraint is just keeping the load balanced. You don't want the plane to be lopsided. The third is respecting the shear limits of the aircraft. Number 4 is paying attention to the fact that the type 3 container, that bigger container that fit into 2 slots, also needs to be taken into account. So all these different configurations. And finally, the total volume of the containers that are assigned to a slot need to respect the volume allocated to that slot. So several inequality constraints. Now, this is how it was presented and framed for a quantum computer. The optimization is presented as a bipartite graph. You see the containers are the red dots, with the slots being in green. This example has 12 edges, right, which we can map to 12 qubits. It's a smaller example because I wanted to show you a little bit more about the flow of the algorithm. So the input data is this bipartite graph, and the output is edges, right? We want to know which combination of container to a slot is going to give me the optimal, most profitable configuration for Airbus. The output from the quantum computer is a string, in this case, of 12 bits. Because we had 12 qubits, the output is a string of 12 bits. The location of the bit tells you which combination you are referencing. If the bit value is 1, it means choose that combination. If it's 0, do not choose. So this was a very clever way to read the answer directly off of the output from the quantum computer. Now, we talked about the input to the problem and the output. What about all the stuff in the middle? You see 2 colors, blue representing the quantum processes and black the classical component. So this is a hybrid solution. The area in black, well, let me start with the area in blue, right? So the optimization loop in this particular situation, in this particular example, is also a loop between the quantum processor and the classical optimizer, right? So the output from the quantum computer is an expectation value that is given to the classical optimizer that gives new parameters, right, for the model, and those parameters are then inputted into the rotation gates in the quantum circuit. The output from the processing can be represented as a histogram, where in this case, the green, right, the green bars represent a higher probability answer, and so these 3 answers were chosen as solutions. And in the graph at your right, I've highlighted 2 of those possible solutions. Now, here's the results from using 28 qubits. You can see right away in the bipartite graph over there, it can get very complicated very fast. So let me focus first on the specifications of the implementation, and then we'll talk about the results in the center. So with 7 containers and 4 slots, we have 28 edges, and so we used 28 qubits. The maximum weight was 23 kilograms, 1,000 shots. That is a function of the allocated time on the system. You could also run 10,000 shots, right? But for this particular result, the researcher had an amount of time allocated on IonQ Forte, and so they chose to run 1,000 shots and got really good results. You may choose to run 5,000 to reduce the shot noise. The optimization took 250 iterations. Notice that there are only 56 1-qubit gates and 56 2-qubit gates. This was part of the innovation we did with Airbus, designing a short depth circuit that gave actionable results, right? Meaningful results to their business. 1 QAO layer, the quantum approximate optimization algorithm, and the whole process ran overnight with 250,000 iterations. So what's important about that is that approaches a typical kind of batch job that we run in industry overnight. So this was interesting to the client that we could make this problem run overnight and the next morning give them some useful results. Finally, the solutions were tested classically, and that 256 should really be 268 million, but it represents 2 to the 28, which is the entire computational space, right, the state space available for any of the answers. Now, in the center, we wanted to show different ways of implementing this, right? One is the ideal in blue. That would mean a simulator. The columns in red represents the result from Forte, where the optimization, the training, and the inference were both done on a quantum computer. And then the green represents a warm start. For those of you familiar with that, it means that you trained on a classical computer, you extracted those the best parameters for the model, and then used those on the quantum computer in the rotation gates in order to do inference. So we wanted to see and basically check ourselves, you know, how the quality of the results. And you see that the red, which is where we really want to be, we want to be using the quantum computer end-to-end, is approaching the ideal. You also see that the algorithm gave 3 optimal actionable items. The one labeled 23 is the maximum weight, so that really is the mathematical best, but it's very useful to offer clients, you know, 3 optimal answers. And we do this a lot in industry, right? Those of you who do classical machine learning, we very often rank several good actionable choices. And then, of course, in the bipartite graph there, I just labeled to remind you that the edges represent the configuration of which container needs to go into which slot. One of the exciting things about collaborating with clients is you have the client's subject matter expert. These are Airbus experts in their domain, teamed with IonQ quantum computing experts, and the result is a whole bunch of innovation, and it's really, really fun. So in this case, we designed a new cost function for this particular use case, which Airbus can reuse multiple times, you know, in their domain. We also, the depth of the circuit is news, frankly, to be able to do this with just 56 entangling gates. It's the first known implementation of a variational quantum optimization algorithm with the size of 28 qubits, 28 excellent algorithmic qubits. And lastly, just to bring home the fact that the possible space of answers is very, very large. And then the whole thing was run overnight with 250,000 executions of the circuit. Oh, and I want to tell you one more thing. So I wanted to share with you some of the innovation that was implemented in IonQ Forte, in particular the laser systems, because this influences our ability to scale the system. In IonQ Forte, we deployed acousto-optical deflector laser systems. These offer 2 advantages. One, it allows us to more precisely target the laser onto the ion. And for those of you maybe new to IonQ, we execute the commands that you submit in Python or Qiskit or Circ. Those commands are then implemented with laser pulses onto the ion. So in this case, with this new system, we can more precisely target the laser onto the ion, which of course translates to gate fidelity, lowers errors, and gives you better result. Another exciting thing is that with IonQ Forte, we decoupled the laser functionality from the species of ion. This allows us to change the species of ion. For example, in the future, we will be using barium ions because they allow us to move closer to room temperature operation. Currently, we use ytterbium. But by separating those 2 functionalities, we can keep the same laser system, just use software to reconfigure how the laser is deployed towards the ion and be able to very flexibly change the species of ion. So in the future, we'll be using barium. And that is really indicative of our roadmap and the ability to scale, become modular, smaller, room temperature, and ultimately rack-mounted in your data centers. And with that, I welcome any questions, and we look forward to collaborating with you.